Good afternoon. This is Dr. Schulman just reaching out. Feel free to email me if stuff gets tough. I'm going to be doing 7.2 today, which is population means. This is probably the closest thing we're going to get to a t-test or chi-squared. So I think it'll be really useful. As I said, when I finish everything, I'm going to make you some t-test videos just because I think they're really useful. My plan is to go through it by hand using the programs and just showing you how we can estimate population means. It's really important to be able to estimate these population means. Why? Well, I think the main reason is it's just we were trying to understand population like parameters before, but like we really care. What do we really care about? We really care about the means of these populations. We really care about the average of what's going on and how we can estimate that from what we have. Uh, but I'm going to share my screen. I'm going to go through the chapter and then I'll do the problems. And let me know if you have questions. So I was grading some late work. And here we go. Oh, sorry. Here it is. So we're going to go to the uh, we're going to go into the modules first. I'll show you where I'm at. I'm down here at 7.2, and then I'll do 7.3, and then I'll do the chapter 7 review. This lab, uh, discussion 3 lab, questions and answers should be next to the discussion lab. Sorry about that. I should change that for the other one. I'm human, right? I make mistakes. That lab was in the wrong place. It should have been on the unit above because it has binomials in it. So I'm going to go to modules. I'm glad people are doing their work. That makes me happy. So where's that discussion? Here it is. The lab should be probably above the exam. There we go. All right, so we're in 7.2. How many questions we have? A whole boatload, right? We got a whole boatload of questions. I'll definitely do most of them for you as usual. All right, so 7.2, the questions. We can go to my math lab and mastering. Open my math lab, and this is gonna open. I guess my session timed out. So we go to open my math lab. Then I'm gonna just open the book. So I'm gonna go to eText. I'm gonna go to Pearson eText. And the book should magically open. Here's 7.2. All right. And I'll also have some notes that I'll be writing along the side, which you can follow along. I'll put this over here. Where are these notes? It's in the bookshelf, Intro to Stats 7.2. Okay, everything's right there. Beautiful, beautiful. So here are our problems, and let's work with it. So the main goal of this section is to present methods for using a sample mean to make an inference by the value about the population mean. That's our whole goal. Let's remember the notation. This is our sample. And we use this sample mean to tell us stuff about our population. So we can't get everybody. So that's where this comes into place. The sample mean is the best point estimate or single value of the population mean. So that's our point estimate. So these are the 3 things we're going to have. The confidence interval, which I did like a million times last video, uses sample data constructed and determine a constant integral around mean u, and the sample size. So we need 3 things. As long as we get these 3 things, the point estimate, our CI, our confidence interval, and our N, our sample size, we should be good to go. we should be able to do whatever formula they have to get that population mean. Let's keep it going. It's rare that we want to estimate the unknown value of a population mean, but we somehow want to know the value of a population standard deviation. Now we focus on a realistic situation in which the standard deviation is not known. So in the past, when we're doing these, we had these population standard deviations to do the problems, right? However, that's not really realistic. Usually we have to find these things, right? We can't just be like, I think it's going to be this. So this is what it is. The sample mean is the best point estimate for the population mean. Because even the best point estimate gives us no indications of how accurate it is, we use a confidence interval, which consists of a range of an interval of values instead of just a single value. All right, so this is the best one, right? The point estimate. And we're going to use that to get a range of the values. The accompanying box includes the key elements for constructing a confidence interval estimate of a population in the common situation where you do not know your standard deviation. So these are everything we need. We have to construct a confidence interval to estimate a population. So we got to use our CI to get what? This is going to force us to figure out our population mean. So we need a bunch of things. Well, this is our notation, our sample mean, our S sample standard deviation. I always use SD for this, but guess what? I'm not going to argue. Our population mean. N is the number of values, the number of our sample. How many people took the survey? You can think about that for little n, and E is our margin of error. You forget about margin of error, it just means we're going to use this to get this number. Sorry, I'll use a different color. Our whole goal is to take this value to get this value, but we're not going to get it exactly, so you have to account for error. All right, these requirements, not nearly as crazy as the last one. As long as we have a what, we just have to make sure for requirements. As long as we have a simple random sample and we have over 30, or it's a bell curve. So as long as it's normally distributed, or if it's bigger than 30, we can do this. And remember, the reason why we can do this for anything bigger than 30 is because of the central limit theorem. If that stuff's still weird for you, just rewatch that video or shoot me an email. Whoa. All right, if the second requirement is not satisfied, we can use the bootstrap resampling method. Honestly, I wouldn't worry about that. All right, so here's our formulas. They shouldn't be too hard. If they are, I'll try my best. So we have our sample mean minus error, our mean, our sample mean plus error. That's the one we're going to use. You could use the other one. Right? You could use this, your sample mean plus or minus E, or use this. How do you get that margin of error? Is that a t-statistic? Do we finally get one? That'd be really nice. We've only used Z before, times S over the square root of N. And then we finally have DF, which equals N minus 1. Remember this N minus 1 comes from so all the way back in standard deviation, because we have a standard deviation one, right? So if we have, this is the sample standard deviation, and this is the population, the formula, just so you know it, is always going to be the summation of X bar, the mean minus X squared. We take the square root of that whole thing and we divide it by N. Or if we have everybody, right, the formula, sorry, over N minus 1, because we don't have everybody, so we have to use this degrees of freedom. The other formula, sorry, I think it's actually X first minus X bar. I believe that's the standard deviation formula. I believe it's x minus x bar. It is x minus x bar. See, I never want to tell you the wrong thing. It didn't look right, that's why. And notice when we have, so this is for our sample. Notice when we have the population, we have everybody. Well, one, we have the full mean. And now we don't have to subtract by n-1. And I'll talk more about degrees of freedom and what it is as we go through this. Let's finding the critical value. And our critical value is t. That makes me so happy for a t-test, which is so nice. The confidence interval is, and the alpha is the complement. So if we're 95% confident, it's due to chance, it would be 5%. We just want to be 5% sure that it is not due to chance. And this is our critical value. It separates from the right tail of the student t-distribution. So we are basically doing a t-test. I was hoping we would get to a t-test because it's like the most most commonly used thing for this stuff. All right. So when using the original set of data values, we round the confidence to one more decimal place than it's used for the original set of data. When using the summary statistics, round the confidence to the same number as used for the sample mean. So basically, whenever we're doing the confidence interval, we need one extra one plus one decimal. That's the best way to think about it. And for your regular ones, so your X bar, your S, it's just going to be whatever the mean is. Whatever the sample mean is that they give you. That's going to be the same thing for decimals. All right. With large samples, then it's common to consider normality to be satisfied. So as long as we have bigger than 30, we could use, because the central limit theorem, we don't have to do anything else. And then with small samples, we have to test for, we have to make sure it's bell curved. It's not bell curved, we can't use it. So somewhat close to being symmetric should only have one mode. Why is that the case? Well, if it's bimodal, this is something that's bimodal. See how it has like two humps in it? That's not something with just one mode. So it doesn't look like the bell curve. And if we have an outlier somewhere, right, like it's gonna mess us up. So this is why a lot of cases in statistics, we throw out those outliers or we regress them to the mean, or we like literally put whatever the mean is for that outlier. So that's just something we could do. We're 95% confident that the interval from 8.591 to 9 actually does contain the true value of the mean. It's just a success rate. That's what it means. And finally, in this section, we use a student t-distribution, which is commonly referred to as a t-distribution, developed by Gossett, who was a Guinness Brewery employee who needed a distribution that could be used with small samples. Wow, we finally get to hear about the person who makes it. That makes me so happy. Let's check out our boy, Bill Gossett. There he is. Gotta love the mustache. He was the head brewer of Guinness. He also came up with the student's t-distribution, originally called the student z-test. Looks nice. Probability students is a continuous probability that generalizes standard normal distribution. It's symmetric around 0. I love it. So if you want to read more about this guy from the 1800s, who spent the rest of his 38-year career making beer, I'm a fan already. All right, so here's our T formula. There it is. We finally get something. So the population is normal, then the distribution of T, or we usually call this the T statistic. All right, so what are all these parts? This is really good. So this is our T distribution. This is our what? Our sample mean. This one is our what? Population mean. This is our what? Sample standard deviation. And this is our what? The N need, the size of the sample. So all that stuff we need. A student is commonly referred to as a T distribution, degrees of freedom. In general, the number of degrees is usually just -1. It's the number of values that can vary after certain restrictions have been exposed. It's a really good definition for degrees of freedom. It's the number of sample values that can vary after certain restrictions have been imposed on a data variable. If 10 test scores have a restriction that the mean is 80, their sum must be 800, you can freely assign the values to the first minute scores, but the 10th score would then be determined. So what does that mean? So we used every single one but one for this. We still get the right answer. This is great. Probably the best degrees of freedom definition I've seen in a long time. And then our critical value. So we're gonna do the critical value just like how we did the z-score. You can use the technology. There should be a table. It does not include the exact number. You could use the closest value by varying it. Okay, so student T distributions are different for different sample sizes. So when it's 3 versus when it's 12, I might as well go to the table. So let's look at table A3. Here we go. Notice it's different between 1 and 2 tails, which is great. So if we have one tail, right? And I spoke about this in the very beginning when I was giving you the intro, but one tail just means we definitely think one's bigger than the other. Like the mean of A is bigger than the mean of B, right? We definitely know. So we're only going to look at one side. Now, if we don't know and we just say the mean of A is not equal to the mean of B, then we're like, I don't really know. So I use two sides. So notice that it's different based on this. We've got our degrees of freedom one side, and then we have all of our values here, which is really nice. If you don't have a specific one, you can just get close to it. But this goes all the way up to if I have 150, but these are pretty good. Can we use technology though? Let's see what technology they give us for this. But this is a great table. I've used it many, many, many a time. All right. So we can use the table. All right. Is there a way to use technology? Probably. It has wider distributions with smaller samples. It has a mean of 0. Okay, and it should have a standard deviation of 1, right? Varies with sample size, but it is greater than 1. Unlike, okay, so the standard deviation is going to change for this as we go through it. Okay, so really keep that in mind. For your T statistics, whenever we're talking about a T statistic, right? First, we got to tell if it's 1 or 2 tail. The other thing we have to know is that the mean is 0, but our standard deviation is not generally going to be 1. It's going to vary. It's going to vary. As the n gets larger, it gets closer. So the more people we get, the closer it's going to be to. Confidence can be easily constructed with technology. Evaluate the margin of error. Use this. Round the resulting. Okay. We finally made it to an example. Who would have thought it? So, oops. Find the critical value of TA corresponding to a 95% confidence interval given the sample size is 6. Okay, so here's our question. They just want the t alpha divided by 2. We've got a 95% confidence interval. Our n is 6, which means our degrees of freedom will be 6 minus 1, so 5. If I go back to our table, I just hit forward. It's so nice. All right, so if I go back to our table, right, it doesn't say if it's 1 or 2 tails, which is kind of, it probably did, but who knows? I'm just going to assume 5%, but we're cutting it in half by 2. So I'm going to assume this is 1 tail of 5%. It's either going to be this value or this value, and we're going to go down to 5. So our answer is going to be either 2.571 or 2.015. Let's see what it is. 2.571 or 2.015. Let's see what the actual answer is. All right, because n is 6 is 95 corresponds to 0.05, so there's an area of 0.025 in each of the 2 tails. Okay, that's cool with me. I like it. And it was a 2.571. I guess we're just going to assume it's 2 tails unless it tells us otherwise, which is totally fine. Boom, boom, we like it. To find the critical value using the table, we go to area 2 tails or 0.025 for 1 tail. Well, that's the way I did it. How do we use technology? I'm going to check out StatCrunch just to see if there's one for it. StatCrunch. Just to see. T-stats. I believe it was 1 sample with data. Okay, I don't have any data, so oops. Where's that stat? T-stats? Oh, maybe if we had a summary. I don't know. No. Okay, so we'll have to just see what happens. It's going to spit out the answer when we put in technology anyway, so I wouldn't worry too much about it. All right, let's find this confidence interval. Listed below are the weights of randomly selected Reese's peanut butter cups. They're from a package of 38 cups, and the package label states the weight is 12 ounces or 340.2 grams. 38 cups have a total of 340.2 grams. Then the cup should have a mean weight of 8.953. Use the listed sample to estimate the mean weight of a Reese's peanut butter miniatures, and we have to do the confidence interval. Alrighty, so let's see what we got for this. So we gotta try to get the mean. So we need the t value to do this, right? It's right over here. So the cup should have a mean weight of 8.953 grams. Based on the preceding results, it would seem that the packages are indicated to be keeping by the label. All right, so let's see what all the things were. So use the I didn't have the listed. I didn't see down here. So this is our listed data. The first thing we have to do is get the point estimate, right? So to get our point estimate, which I'm assuming is just our basic X, in this case, yeah. So I'm gonna first just find the mean of this thing. I'm gonna take these numbers and find the mean. Let's get a new sheet going. 8.639. 8.689. 8.548, 8.980, 8.936, and 9.042. The first thing I'm going to do is just get a sample mean. And to get the sample mean, I'm going to add up all of these values and divide it by the total, or I'm just going to do equals average. That's going to be my first step. 8.8057. 8.8057. So that's what we're going to use. 8.8057. I like it. B is use the listed sample to construct a 95% confidence interval. Okay, so how do we get that CI, that confidence interval? Confidence interval. I believe we just add or subtract. We did it last time. Forgot the formula off the top of my head, so I'm going to look at it the first time. Before constructing the 95% contract, we must verify the requirements. Oh yeah, we only have 1, 2, 3, 4, 5, 6 pieces of data. That's not enough. So we have to see that it's if it's normally distributed. So in the accompanying normal quantile plot. Okay, so let's make a normal quantile plot. Take the data, drop it in here. I believe it's on your graph, QQ plot. Let's see what we got. Oof, is it a straight line? I don't know. It's looking kind of close. That's what I got. The data appeared to form an anomaly. All right, if they say so, right? Doesn't look the best to me, but I'm not gonna. I guess it's close enough to a straight line. What can we also do? We can just make a quick histogram of this thing. I guess it looks like it's kind of making that move. There's just nothing in the middle. I'll take it. Okay. I'm not going to argue with it, but yes, we should be checking these things. I'd love it if it was more of a straight line, but I think it's because the decimal is so small. All right, technology B can be used to automatically construct the confidence interval. Oh, well, isn't that nice? How StatCrunch gets the confidence interval. All right, so let's do it. A one sample T confidence interval. Now we have data, right? First, find the critical value from table TA3. Oh, okay. Nice. I want to be able to do this thing by hand. And that's the most important thing to be able to do with this stuff. We have the sample mean, which we got before, the 8.0587. We got the standard error. We got the t-stat. We got the p-value. But they say we could also get the 95% confident interval results. If I do this, yeah, it does give me the lower limit and the upper limit. Wow, that's really fast. That's nice. That is nice. So we know what the answer is, right? But we might as well do this thing by hand, right? We're all smart here. We should be able to do this whole thing by hand using the formula. All right, so let's get to the formula. We first know that our t, we have to get our t statistic. We know that we want, so the first thing I need to do for this formula is figure out what t is. That's what I need. And the t we know it's got to be at 95%. So this is the first thing I'm going to do. Now I'll go back to the formula. The first thing I need is that t statistic. We know it's 95%. We know our degrees of freedom makes this a 5. Wait, is it a 5? Yeah, it is 5. All right, so let's look at this thing that we got. All right, we want 95%, so that's 0.05. Degrees of freedom is 5, 2.571. That's our t statistic. Whoa, wild. Okay. Okay. None of these want to be my friends. This is an old one. Sorry about that. I haven't typed it. There it is. All right. Where are we at? Get the error. Going to be our t statistic times standard deviation over the square root of n. So our error is what? 2.571 and the standard deviation over the square root of 6. What's our sample square root? Well, if we don't know it, that's okay. We can just get it. STDEV dot S, which is because we have a sample. This has the m minus 1 at the bottom of the formula, so it's 0.205433. Six. So there's our standard deviation. And then for our error, I'm assuming it's this 2.571 times parentheses, because we have to divide, sorry, equals 2.571 times parentheses, this guy, divided by square root of 6. All right, I got an error of what? 0.21. 21. Remember, it should always be one more than the means. 6. Our mean was 8.8057, I'm pretty sure. That's what they had, or 8.806. But we're just going to have to add or subtract this 0.2156. So it's going to be about 8.6 to 9. That's what I'm guessing, 8.6 to 9. Let's see what it is. Okay. 0.21. That's what we got. 0.2155. 8.6 and 9.0. I love it. So I got the right answer, which basically means we have 8.5901 grams for the mean, the 9.0213. This means we are 95% certain that the mean falls between these values. Boom. And let's look at the StatCrunch answers. 8.59 and then 9 point, yeah. So you could do it by hand. You do it by StatCrunch, either way you're gonna get the right answer, which is always nice. All right. Bootstrap resampling. So the basic approach is to use technology such as that is to resample these. If we repeat this, we'll get it. All right, let's try one of these. Listed below are the sales in millions for vinyl LP units. The sales are listed in order of years. We have 30. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 25, 26. Oh my God, so close to 30. Okay. The confidence, a good tool for gaming this. If I put it all out using the Q sort, it might not be right. Is not a good tool for gaining insight of the data. All right, so it's off. So we can't use this. Oh, because it exponentially increases. So it's not a normal curve. Let's look at the data. Really small, really small, really small. And then right here, yeah, it gets really big over time. And remember this, we used this data before for something. So if you look at the data, it's definitely not a normal bell curve. Sure, if we look at the Q sort thing, do I want to type them all in? I guess I could type them all in. Type it. They're pretty small numbers. We'll use the Q sort to tell that this data is not the best data of the datas. So here we go. 0.3, 1, 0.6, 1.9, 0.8, 2.5, 1.1, 2.8. Oh, but it has to be in order. All right, sorry. 0.3, 6, 0.8, 1, 4, 1.4, 1.5, 1.2, 1.2, 1.3, 1.4, 1.2, 0.9, 0.0, 1.9, 2.5. Here's where it gets crazy. 2.8, 3.9. I don't think we need to do it in order. 13.1, 14.3. So I think the last one's 16.8. Gotta love inflation. All right, here we go. Oops, not bad. Oh yeah, that does not look like what we want. So cool. As you can see, this is not the line we were looking for. Finding a point estimate and margin of error from a confidence interval. So this is the same thing we did before. Upper plus lower divided by 2, upper minus lower divided by 2. I assure you that I've written these before, but I'll write them again. So our upper CI, I usually like writing it this way, CI with a subscript plus CI lower with the subscript over 2, and this is for a margin of error. CI, and this is the minus one, right? Yeah, CI upper minus CI lower divided by 2. Sorry. Figure 7-6 shows a confidence interval. People smoke, people don't smoke, but are exposed to it. Okay. People not exposed to smoke, people exposed to smoke. Smokers. All right. So sometimes we do know the standard deviation. So this one we do know it. We can use the z-score. Nothing crazy about that. when we do not know when the standard deviation is not known and it's bigger than 30, we're going to use the t-distribution. Cool. So the t is when we do not know the standard deviation, and the z, or the normal, when we do know the standard deviation of the population, because we could always calculate it, right? Right? This is what we need. Like, because we could always calculate it based on our sample, but we're not going to know that. And then we use this bootstrapping method if it's not normally distributed under this. All right. Oh, we're almost at the bottom. We want to know how to collect a sample to be used for estimating population. How many samples do we need? I would use a G-power analysis, but let's see how they want us to do it. Determine the sample required to estimate the value of population. I'm going to use the z-score. Okay. All right, so here's our formula. New formula. Okay. This is for getting n. This is for finding out exactly the sample size we need to run the study. So we take our z-score with the alpha over 2. So that's just the right-hand side. We're going to take this is the population, right? Then we're going to put this over the error. I'm going to square the whole thing. That's what this means. You always have to go up for sample size because it's usually people or animals or something. The rounding must be a whole number. So dealing with an unknown population standard deviation when finding the sample size, we substitute a known value for the population standard deviation when it's unknown. So we can use the range rule of thumb, which I hate. So other ways to do this when we do not. So this is the case when we do not have. Sometimes we do not have the population standard deviation. Okay, sometimes we just don't have that. So we can take the range and divide it by 4. I hate this way to get it. Start and improve the process. So start the question without knowing it and using it several times. Okay, so that's way. The prior results is probably the best way. I would go with 3. If this was me, I would use prior results. Use some old test. That'd be the thing I would do. Go figure. Robocalls in recent years, there were 15, 16 every second. There were in the year this. Okay, that's exciting. All right, so my bad. Assume we wanted to estimate the mean of IQ scores for a population of statistics students. How many statistics students must be randomly selected for an IQ test if you want to be 95% sure that the sample mean is within 3 IQ points of the population? So 3 IQ points, that's the error, right? So right away, we know the error. So we already know our error is going to be 3 IQ points. So I know my error is going to be 3 down here. We want to be 95% sure. So we need to get our z-score. Do I have to use the table? It's this one, 1 sample. Did I forget how to do it already? Z-stats, 1 sample with data, with power sample size. I don't know. No, because I don't have it. I guess we use the table. You're forgetful like me. Oh no. I wasn't using that. I was using this. Now I remember what I was going to do. Equal, normal, normal, dot inverse. That's what I was doing before. Probability is 0.975 because it's a little bit more than we want just from the right hand side, from the right hand point all the way over. Our mean is always 0. Our standard deviation is 1. It is 1.96. 1.96 the number we need. All right. And I don't have a standard deviation. Oh, we're gonna just use that it's usually 15. That's kind of cheating. But I'm cool with that. We square the whole thing. As usual. Whoa. Sorry about that. As usual, I'm gonna use Desmos for this. I'm gonna do 1. So parentheses 1 point. So double parentheses 1.96 times 15 divided by 3. I'm gonna square it. 96.04 people. But guess what? Even though I have 0.04 per person, we always round up. 97 should be the answer. Let's see what they got. Yes. All right. Wait, am I already at the end? Oh, man. Okay. I thought we'd have some more examples, but I guess we're doing them. Hopefully this was useful so far. Let's go 5 through 7, 10, 15, 16. We're not actually doing real t-tests, what makes me sad, but that's okay. 5 through 7. Identify the critical value of t. Find the margin of error. Find the confident estimate of u and write a statement. Wow. Okay, so these are all, everything. I'm going to start with number 5. Excuse me. Actually, pause one moment. I'm going to grab some drink. All right. Let's make this magic happen. So we got birth weights. We have an N of 36, sample mean of 3,150.0 grams, sample standard deviation of 695.5 grams. We want to use a confidence interval of 95%. This means our degrees of freedom right away is going to be what? Well, we have 36 minus 1 is 35. That's our degrees of freedom. This is going to give us what we need. Should we try to use the stats or the table? Let's use the table first, and then the next one I'll use the stats. So I'm assuming since we have all the data, we could just do it in StatCrunch. So let's go right to table. $135, which is here. We want to be 95%, two tails, so we're in the middle. Unless they're like, we definitely want less weight. But I'm assuming the degrees of freedom, we're just going to make this a 2.030. All right, and then all we need to do is the formula, really. They get the confidence interval, we can just use this guy, which is too crazy. We have M, so it's just E to Z, standard deviation over square root of M. But we don't have that value. So I think we need to do We just have to get the error first, which is S over square root of n. The error is going to be S over square root of n, and we're going to do t statistic times that. So we know that this is 2.030 times our S, which is 695.5 over the square root of 36, which we know is just 675. All right, cool. Let's make it happen. 2.0030 times parentheses 695.5 divided by 6. And we ended up with 235.311. 235 point, this is our error. 235.31. Since this is all to 1 decimal place, this should be to 2 decimal places. So our confidence interval is going to be 3150.0 plus or minus the error, which is 235.31. This means we're 95% sure that it falls within this range. 235.31. I believe this is the answer. And what else? Okay, I could look in the book. It says that t statistic is 2.030. That's what we got. It says the error is 235.3. That's what we got. Sorry, they just used 1 decimal place. And the confidence interval. Oh, they actually did both of these. So guess what? I might as well write it out. So our mean is 3150. 315. Oops, sorry. 3150 plus. You could write it the other way. I'm just going to show you how it's in the back of the book. So the first one is going to be, well, this is the upper limit. And the lower limit, I just have to subtract it. This means we are 95% sure that the mean's going to fall between these 2 values. That's the answer. Now let's let StatCrunch do the whole thing for us, right? Because it should be able to do everything for us and we shouldn't have to use our brains at all. This is why it works, okay? This is why it all kind of works for us. You don't even have to do the table. All right, so let's go to stats, t-stats, 1 sample with summary. Our sample mean was 3150. Our sample standard deviation was 695.5. Our sample size was 36. We're being 29% confidence interval computes. Degrees of freedom, lower limit 2914, 2914, upper limit 3385. Wasn't that easy, right? All right, let's do the next one. We'll do the next one with the stupid table, so we don't have to think. Here's 6. All right, n is 32. X bar is 4.521. Our sample standard deviation is 0.1077. We want to be 99% sure for our confidence interval. So we can honestly just type this in right here. Oops. Now it is 4.521. Our standard deviation is 0.1077. Our sample size is now what? Sorry, 32. But they also want the degrees of freedom and stuff. So your degrees of freedom is just one less, 31. And I'm gonna see if I could just get that value by just looking at it, okay? Because they also want the error. And they also want the t statistic too. So we got to get these three also. That changes to 99. It has degrees of freedom. Is that the standard error? I don't know. But we have the lower limit and the upper limit. So we know that it doesn't give us the statistic, which is kind of a shame. So we actually have to look at the table for that. This final answer is going to be 4.469. They give us this one? No, they don't. That's okay. 4.573. To get the error, we could just take the lower and the upper bounds and put it around the mean and just see how far it is away, or just subtract one of them. What do I mean by that? So I can just take the mean 4.521 and subtract 4.469, so that I already know the error is 0.052. And how do we get that t statistic? It's weird it doesn't have something for the critical value. You think it would, right? Let's see if I can do equal t distribution. Our x is 32, right? Our degrees of freedom is 1. And I want the cumulative. Let's see if this works. No. Oh, I just have to write true or false. Okay. Let's see if this works. I don't know. All right, well, what's one that we did? We got this to be 2.030. Let's see if this works. So equals t dot distribution. This is left tail, that's what we want. And okay, so the first one is our x. Require the numeric value to evaluate this. So I believe this is going to be our mean. Our degrees of freedom, in this case, is 35. I'm going to go with true. See what happens. Okay, so what is the x? Oh, they're asking us for that critical value, but we have to find it, right? Students left tail distribution for 60 as a cumulative 1 degree. Oh, it's the inverse of this. Let's try it. Equals t dot inverse dot 2t But we just want the critical value. This is if we have both arrays and the amount of tails and the type. Okay, this is if we have the data. So they'll let us do it if they have the data. Well, guess what? I'm just gonna have to use the chart. Sorry about that. I hope that's okay. We're using the chart. All right, so for this one, we need the chart. We already have the answer, but we need the t-statistic for the chart, which is 31 degrees of freedom with a 31 degrees of freedom in the middle. 2.040. That's what it was last time. 0.030. All right. I'm gonna do this next one completely by hand. And that's fine. Here we go. So here's number 7. Your n is 36. Your sample mean is 0.8240. Your sample standard deviation is 0.00570. We want this for, so our degrees of freedom is 35. We want to do the confidence index or the confidence level 99%. So we need our t-statistic. We need our error. We just put it in. So first thing I'm going to do is move the chart. So 35 at 99%. So 99%. We're going 2 tails again. So ready? 99% is right here. That's what goes on the chart. So I have to just go down to 35, which is 2.438. Now to get the error, remember, it's just a t-statistic, right? Times the standard deviation over the square root of n. So the error is 2.438 times S, which is 0.00570, divided by the square root of 36, which we know is just 6. So 2.438 times parentheses 0.00570 divided by 6. So this is our error. 0.0023. I'm going one more of these, okay? But it could really just be 0.002 because they want these all to match. Like they want it to match the mean. Oh, the mean is 3, 4, 5. So 1, 2, 3, 4, 5. So it's 0.232. That's what we should have. So it's going to be 0.82410 plus 0.00232. So this is just telling us that our final answer, so we're going to be 99% sure that the population mean is going to be between 0.8 to 6.4. Sorry. 0.8 to 642. And the other side, I just have to make this a minus. .8 to 178. And I can check these because this is number 7. All right, so it said our t-statistic was wrong. It said the t-statistic should be 2.724. That's not what I got, 2.724. So we all make mistakes, right? 35, and it's 99%. Okay. 99%. It's over here. I was in the wrong column. That's 0.01 for 99%. My bad, because we should be in two tails. We all make mistakes, right? So for 36, it should be 2.719. That's what I got. 2.79, which changes this value. So it's 0.00258. Error. 0.00258. So this is 0.00258. So we know it's going to be between 0.82152 and 0.82668. 0.8266. Oh, rounded up. It is rounded up. It is 0.82669. My bad. So now these are all right. I'm just gonna see. Find critical value. So that's all I really care about. Open Excel, use this. Probability, okay, it's 95%. That's all you have to do? Okay, I'm gonna try it again. I think I need data for this though. I'll do one with equals T dot INV dot, I'm assuming it's for two-tailed, right? Our probability for the last one was 0.99. Maybe I didn't put the decimal. Our degrees of freedom was 35. Let's see if this works. 0.0. No, it's not right. 0.99, 35. What if it's 0.995 because it's halfway between? Nope, not getting it. Should be getting 2.719. We're not getting that value at all with this probability. Degrees of freedom. Yeah, okay. Find critical value of T statistic in Excel. About so oh, it's the other way. It's the other way. Ah, it's the alpha level first. That is so annoying, and I'm not happy about it. So T dot I, so equals T dot INV. I believe we have a two-tail And it's gonna be 0.01 at 35, 2.72, 2.7238, 2.719. I don't know. Let's just make it a one tail and see what happens. Nope, that's it. I guess it just rounds it differently. Yeah, 2.72, 2.72. I'll take it. It's close enough. Let's try this one. I would recommend just using the table. It's inverse, right? Correct. T dot inverse. Okay, so T equals T dot inverse two tail. All right, let's see what we got. Our probability for this one for 6 was 0.01 with a 31 degrees of freedom. 0.74. No, 2.04. Yeah, so I don't know. I would just stick with the table. Excel doesn't seem to be doing it for you. So guess what? You're gonna have to use the table. I'll look, see if I can look up another way. But let's just keep going with these. All right, 10, 15, 16. There's number 10. The thing is, it automatically spits it out when it does it, which is why I don't know why it's being so difficult. All right, let's look at 10. Maybe this one will be nice and hard. Find the confidence interval, estimate of the mean. All right. Excuse me. In a weight loss program, is that 40 adults? Yeah, 40 adults. Okay, so our N is 40. For 12 months, their sample mean weight loss was 2 pounds. Sample standard deviation was 4.8 pounds. We want a confidence interval of 90% to estimate the mean weight loss for all such subjects. Does it appear to be effective? Does it appear to be practical? They're losing like a pound. It's not going to be practical. Okay, so let's see how we're going to do this one. So we know it's a 90% confident interval. We have degrees of freedom of 39, right? The first thing I want to do, I can get this T statistic with 39 and 90%. So here we go for two tails, 90%. So we're in this fourth column. And I want what? 39. So I have 1.685. Okay. That's cool. Construct the confidence interval estimate of the mean. So this is just a sample standard deviation. So all we need to do is find the error, which we were doing before on top. So the statistic over standard deviation divided by square root of n. So we have our values. So it's 1.685. We know that our sample standard deviation is 4.8. know that our n is the square root of 40. So we have a 1.3 pounds there. What does that mean? This means that we're going to be we're 90% sure you're going to lose between 2.1 plus 1.3. So 3.4 and 0.8 pounds. We're 90% sure you're going to lose between a pound and 3 pounds. I don't know how practical that is. So I don't think that's practical. So that's going to be my answer for number 10. I think that's the answer. That's our confidence interval. We're 90% sure this is the answer, but that is not the value we're looking for. I mean, like, you want to be losing more than 1 pound, 1 to 3 pounds. Now let's look at 15. Oops. Again, 15 is construct the confidence interval estimate of the mean. We just did that. Just make sure that's just the little s. Yeah, it is little. I just like to double check that. So make sure it wasn't the population standard deviation for all these. All right, 15. Got some data. So we only have 15 commuted. Constructors. Well, the first thing I want to know, is this a normal graph? So I'm going to do a QQ plot. For number 10, we had 40 adults. So this was good. Why was it good to use? Over 30, and our n was over 30, right? Our n is bigger than 30, so that's why we knew we could use it. It just wasn't practical. For number 15, I got to test this and make sure that these make sense. So let's break out the crunch. I'm just going to put a new variable. 5, 25, 45. 5, 5, 40. 25, 8, 50. 5, 5, 30. 15, 25. 15, 25, 50. All right, let's look at this thing. I think it's pretty close. I think it's pretty, I don't know, pretty close. We're going to take these and put them in a histogram. We're going to start at 0, right? We're going to make the width what? 5 each? Let's see how it looks. I don't know. I don't like it. I'm not the biggest fan of this data. I think this is skewed. I think it's skewed. So I wouldn't use this for 15. I think 15 isn't good. So I'm not going to use it. I'll still get the answer for it, but I don't want to use this data. I don't think the picture looks right. So that's what I would say. I'm saying it's not a normal distribution. So we can do a stat, a t-stat, one sample with data. We can put this whole thing in, right? Variable 2, the confidence level, we wanted this at what? 99. I want to click compute. All right, we're gonna be between 9.22. Wait, sorry, we're gonna be, it's gotta be the same, right? The mean is 22.5, and we're between 9.2 and 35.8. I'll look it up. 9.2 and 35.8. Yeah, there we go. The book said it sucked too, so. So we could claim that we are, what was it, 99% sure it falls within this range. But it's not normally distributed and our n isn't bigger than 30. So we wouldn't use it. All right, let's do one more. I feel like that was the best example so far. I'll do 16. Here's 16. 16. Now we have 32 of these things, so we can use it, right? Isn't that nice? So now we're able to use it. So it doesn't matter. So let's say this one also looks ugly. It doesn't matter because of the central limit theorem. We have over 30, so it'll work out. Let's make it happen. 5, 25, 25, 45, 45, 75, 5, 60, 5, 40, 40, 25, 25, 8, 8, 50, 50, 10, 5, 10, 5, 30, 30, 15, 15, 25. 25, 50, 50, 20, 18, 30. So I'm supposed to have 32. I have 32. I'm good to go. First thing I'm going to do is I'm going to graph the histogram of this. Variable 3. I'm going to start this at 0. Since we're going all the way up to, what was it, like 60 or something, and make them 10 each. Compute. Still right skewed. Still right skewed, but we have over 30, so we can do it. If I do my QQ, could fall on the line. It's not going to. It doesn't really seem like a line. It's pretty close though, not gonna lie. I don't like this QQ business, but we're all, it is what it is. So all I have to do is go to, I believe t-stats, one sample with data. Variable 3, we want this at 99% confident interval. Ooh, here it is. Show critical value. So we can use this and we can click show critical value. That's how we can do it. Wow, took me a long time. So don't use Excel, use this, and it should give you the critical value every time. So that's nice. I'll write the answer for this one, and then I'm going to show you how to do it for the rest of them. So the answer for this is 18.3 is less than the mean, which is less than 36.3. We are 99% sure it will fall between this for your commuting, your daily commute. That's your commute time. All right, let's do this. I knew I'd be able to figure out how to do these and just get the value. If I have this data, right? Data, t-stats, one sample with summary, boom. Our sample mean is 3150. Our sample standard deviation is 695.5. Our sample size is 36. Our confidence interval is 95. And we can show the critical value. Our critical value is 2.030. Critical value 2.030. Cool. I knew there should be a way to get these things exactly. Let's do this one. Let's do 7. Let's now make the sample mean 0.82410. Sample standard deviation is 0.00570. We still have 36. This is now a 99% confidence interval. We click that compute button, boom. And we now have a critical T of 2.72, which is the same thing, 2.719. I think that's what we got on the Excel one for this, but I'm not even gonna question it. I'd use this one every time, whether you have the data, whether you have the data, whether you have the summary, you'd be fine. I might as well just look at number 22 for you guys, make sure it's the same sort of thing so you don't freak out. Find the sample size required to estimate the population mean. All right, so remember when we're doing these sample size, we just use this formula. So see the preceding exercise. So I'll do 21 then for everybody. Sample mean is 100. Well, this is what we have. So z-score. And then we have this. And then we divide it by e. So z-score, standard deviation divided by e. So I'll do 21 just to get you going for the next one. So we want the n, which is the z-score. Then it was z-score times standard deviation over the error squared. So I'll do this one. So that the mean is 100, the standard deviation is 15. We want a 95% confidence interval within 3 IQ points of the true mean. So this says we have a 3 error. That's our error right away. The mean for this population is clearly greater than 100. The standard is less than 15 because a group with less variations. And if we use the 15, right? If we use the 15, we're being conservative. Does the sample size appear to be practical? All right, so all I need is my z-score. Get that z-score, normal dot inverse. So normal dot inverse. Our probability was, just have to shift it a little. They said 95%. Our mean is always going to be 0. Our standard deviation is going to be 1. Why? Because that is for the z-score, 1.64. So that's all I'm going to do is 1.64 times the 15. (1.64) times 15 over 3 squared, 67.24. So this is going to be 68 because why? We always have to round up for people. I'll look it up. 21, right? It says 97. That's a problem. So there's a mistake here. We're going to find it. Could be the z-score. It could be one of these things. So let's see where the error is. Oh, I did 95, but I always have to go 975 because it's always to the left. I should use the table. This should be 1.96. Great. It's 96.04. Is that what it says in the back of the book? Yep, because you have to round up for the extra person, 97 people. Is that practical? No, I don't think that's enough people to do it. I think you need more than 100 people for something like this because one, it's less than the standard deviation of what we were looking at, right? It looks like I got rid of it for some reason. So I guess the moral of the story is use the tables. The programs get a little tricky. The tables will be your friends. I don't see why 96 is too small. Then I'll do the next one. So here is your book. We want to know why 96 is so off. I'm in 7-2. I just did number 21. I think it's pretty small. I think it's pretty small to have less than 100 people for something as large as an IQ test that you want for like everybody. I think it should probably be in like the thousands or something. So try 22 and the rest yourself. That's what I'm going with. So for that Z-score, oh, weren't we using I believe StatCrunch had a one also, right? Let me just show you how to do it on StatCrunch since I made a couple mistakes today. Right? Are we all human? Yes, we are all human. So just to show you how to get the Z-scores. Z-stats, one sample. We just need normal. That's all we need is the normal picture. Maybe it's just under data. That's not right. I know I can't seem to remember where it was. Ah, so it's under calculators. So it's stat calculators, normal. Okay. So this is the other way to do it, right? It's not to get the t-scores. You can't do the t-scores this way. You have to use the data for that. But at least to get your z critical values, remember it's going to be z. This is your mean, this is your standard deviation. And the last one we did was what, 99%, right? 0.99. Um, 0.975 with a mean of 0 and a standard deviation of 1, mean of 0, standard deviation of 1. Oh, because it's 0.95. Haha. We want it the other way because it's always to the left of it. Should be. Did I really forget how to do this? Yes, I did. Wow. Cool. Sorry. So I guess because it's a little hot and I've been thinking for a while. So to get those X values, the critical values for this, you can just go to stat, calculator, normal. This is going to come up. I'm in standard, so we want everything to the left of it, which means it's going to be that 1.644 for the value. The other way to do it, and this was, why do we have 1.95? I'm gonna look back in the notes and see what happens. I'm going to the standard normal distribution. All right. Show the critical value. They say it's 1.96 for n of 32 and a 95%. So let's do this. Calculator, normal. We know we have we know that we have a critical value of 1.96. 97.5. Oh, I think it's because I wasn't dividing by 2 for all of these. We just want one of the sides, because if it says 95%, we just want for the left. We have to double it for the sides. I keep forgetting to divide by 2. That's the mistake I was making. So yes, you can use this normal one. Sorry for the mistake. I knew I'd get it for all of them. Sometimes it just takes me a minute, you know. But yes, you are allowed to use this calculator for it. Let me know if you have more questions. 1.96, 97.5, it's all mentioned. When they say it's at 95, it's 5, but it's cut into 2 pieces. So that was my mistake that I kept making over and over again. Sorry for the error. Good luck with everything. Try your best on the last 4, and let me know if you have questions.